Welcome everyone. Today we turn to a model family that is specifically designed for data that lives on networks rather than on grids or sequences, graph neural networks or GNNs. This topic sits naturally in our global health course because so much of biomedicine is relational. Molecules, proteins, patients, symptoms, diseases, and even the spread of infections are all fundamentally about connections. By the end of this lecture, you should understand what a graph is mathematically, why standard convolutional and recurrent architectures struggle on graphs, how the message passing framework lets a neural network learn on irregular structures, and how specific models like graph convolutional networks, GraphSAGE, and graph attention networks actually work. Let's begin by placing GNNs inside the broader deep learning landscape. Here we're reminded that deep learning is much more than CNNs, RNNs, and GANs. It shows a panel of architectures often used in biomedical discovery, arranged around a central triangle of disease, target, and drug. Panel A is a graph convolutional network, or GCN, showing an input graph passed through a hidden layer with a ReLU nonlinearity to produce an output graph. Panel B is network embedding, a knowledge graph embedding, where a network is mapped into a continuous embedding space. Panel C is an autoencoder with an encoder, a compressed code, and a decoder. Panel D is a standard deep neural network with fully connected hidden layers. Panel E is a recurrent neural network shown unfolded across time steps. And panel F is a convolutional neural network with convolutions, subsampling, and a final fully connected layer. The key message is that the right architecture depends on the structure of your data. And today, we focus on the graph-based family. So let's formally enter the world of graph neural networks. Take a moment here to reset your mental model, because we are about to move away from fixed grids and ordered sequences toward flexible, irregular structures. To appreciate why graphs need their own architecture, let's review the architectures we have already seen. Here we lay out the neural network architectures covered so far in the course. On the left are the data modalities we have handled: text, audio, images, electronic health records, or EHRs, signals, and omics data. On the right is a standard feed-forward neural network taking those inputs and producing outputs. The point is that each of these modalities has a regular structure. Text and audio are sequences, images are grids of pixels, and tabular EHR data has fixed columns. And our previous architectures exploit exactly that regularity. Now we add the modality that breaks this pattern. It's the same panel we just saw, but with one crucial addition on the right: graphs. Unlike text, images, or signals, a graph has no fixed size, no natural ordering of its nodes, and no consistent number of neighbors per element. That irregularity is precisely why we need a new architectural approach, because feeding a graph directly into a standard feed-forward network does not respect its connectivity or its symmetry. This is the core motivation for the entire lecture. Everything really does depend on the data structure. The point here is made explicit. The choice of model architecture is dictated by how your data is organized. Grid-structured data invites convolution, sequential data invites recurrence or attention, and relational data invites graph-based methods. Choosing an architecture that matches the underlying structure is one of the most important design decisions in applied machine learning. So why is the field investing so heavily in these other architectures right now? The answer comes with data, a chart of ICLR keyword growth from 2018 to 2020, from Jure Leskovec. The bars show the percentage of conference keywords for topics like graph neural network, adversarial robustness, meta-learning, transformer, neural architecture search, self-supervised learning, BERT, NLP, and continual learning, colored by year. Notice that graph neural network sits right at the top, with striking growth from 2018 through 2020. The takeaway is that GNNs are not a niche curiosity. They became one of the fastest growing research areas in machine learning, which is a strong signal that they solve real problems. Now let's look at where graph-structured data actually shows up. Here we see 10 examples of graph-structured data, with an important caveat in the corner. Standard neural network architectures don't work well on this type of data. In the top row, we see image graphs, text graphs, physics graphs, spatial maps like transit networks, and agent interactions such as a susceptible infected recovered epidemic diagram. In the bottom row, we see social networks, knowledge graphs, biological networks, molecules, and processes represented as state machines. The unifying idea is that in every one of these cases, the meaningful information is not a single fixed-size vector, but a set of entities and the relationships between them. That is exactly what a graph captures: nodes for entities and edges for relationships. Graphs are not a new idea. Their origins go back nearly 3 centuries. Consider the story of the origin of network graphs in the mid-1700s. On the left is the city of Königsberg, which had 4 main land areas connected by 7 bridges. The famous question was, can you walk through the city crossing each bridge exactly once and return to your starting point? In the middle, we see Euler's insight, that the only relevant information is the land areas and the bridges connecting them, not the geography or distances. On the right, this becomes the origin of graph theory. Euler abstracted the problem into nodes and relationships, creating generalized rules that apply to any connected system. This abstraction, throwing away everything except entities and their connections, is the foundational move behind all of graph theory and graph neural networks. Let's look at that same problem rendered directly as a graph. This hand-drawn figure shows the 7 bridges of Königsberg, now Kaliningrad, Russia, over the Pregolya or Pregol River. Each node represents a section of land, and each edge represents a bridge to cross. Each node's degree is the number of edges connected to it. The annotations label degrees of 5, 3, 3, and 3. Euler used this graph to answer the question, can you walk through the city and cross each bridge only once? The answer is no. Every node here has an odd number of degrees, and that is the problem. To traverse and return, all nodes, except the start and end, must have an even number of degrees. This is our first real lesson in reading a graph. Degree, connectivity, and the parity of connections carry genuine mathematical meaning. Graphs are also central to one of the most famous stories in the history of global health. Here's a question to consider. What is this map, and why is it important? On the left is a detailed street map of a district of London, and on the right is an electron micrograph of a comma-shaped bacterium. These 2 images set up a classic case study that connects spatial networks to epidemiology, which we unpack on the next slide. This is John Snow's cholera map of London in the 1800s. The map is overlaid with a heat map of cholera deaths clustered around a central location, a portrait of John Snow, a photograph of the Broad Street water pump, the cholera bacterium, and a bar chart of cholera deaths per day. The bar chart annotation notes that the handle was removed from the Broad Street pump on September 8, 1854, after which deaths declined. This is a landmark in epidemiology. By mapping cases spatially and reasoning about the network of water sources, Snow traced the outbreak to a single contaminated pump. Conceptually, he was doing graph reasoning, connecting cases to shared sources. Long before we had the formal machinery, and it is a reminder that relational thinking has always been at the heart of public health. Now let's build the vocabulary we need to work with graphs formally. Let's introduce some graph theory nomenclature. A graph, denoted capital G, is made of nodes, denoted N, and edges, denoted M. Panel A defines the 2 basic elements, a node, which is an entity, and an edge, which is a relationship between 2 nodes. Panel B contrasts unweighted graphs, where all edges are equivalent, with weighted graphs, where thicker edges carry larger weights. Panel C contrasts directed graphs, where edges have arrows indicating direction, with undirected graphs, where relationships are symmetric. Panel D shows node degree, the number of edges touching each node, labeled here as 1, 3, 2, and 1. Panel E shows graph density at 3 levels, 0.29, 0.57, and 1, where density measures how many of the possible edges actually exist. The formulas in the corner give density. For a directed graph, d equals 2, m divided by n times n minus 1. For an undirected graph, d equals m divided by n times n minus 1. Panels F and G show degree centrality and centralization, contrasting a star with centralization equal to 1 against a fully meshed graph, with centralization equal to 0. These concepts, nodes, edges, weights, direction, degree, density, and centrality, are the descriptive statistics of graphs. Let's continue building this vocabulary with different graph types. Here we contrast 3 structural categories. A simple graph is one where any pair of nodes can have only one relationship, or edge, between them. A multigraph allows node pairs to have multiple relationships between them, so 2 nodes can be connected by several parallel edges. And a graph, sometimes called a pseudograph, allows multiple relationships between node pairs, and also allows nodes to loop back to themselves with self-edges. These distinctions matter in practice. A patient similarity network might be a simple graph, while a knowledge graph relating drugs, diseases, and genes, through many relationship types, is naturally a multigraph. Now let's look at some characteristic global topologies of graphs. Take a look at 3 important network archetypes. A random graph has average distributions with no particular structure or hierarchical pattern. A small world graph has high local clustering and short average path lengths, often with a hub and spoke character. This is the famous 6 degrees of separation property.
A scale-free graph has a hub and spoke architecture preserved at multiple scales and follows a power law degree distribution, meaning a few nodes have very many connections while most have few. Many biological and social networks, including protein interaction networks and disease networks, are scale-free, which has real consequences for how information or infection spreads through them. Now for a bit of fun that also makes a serious point about the power of graphs. Titled, Graphs Are Genius, this slide references the film Good Will Hunting, starring Robin Williams and Matt Damon. On the right are two frames, the character solving problem 1, a set of tree diagrams on a chalkboard, and problem 2, a chalkboard filled with graph equations. The point is that the legendary impossible math problems in that film were graph theory problems. And that graph theory, far from being obscure, underlies deep and beautiful mathematics. Let's actually look at what problem 1 was. Problem 1 reads, find every homomorphically irreducible tree of degree 10. That is, irreducible trees of 10 nodes that are non-isomorphic to each other and have no vertices of degree 2. The layout marks 4 candidate tree structures as not allowed, allowed, not allowed, and not allowed. At the bottom, a helper figure contrasts a non-homeomorphically irreducible tree with a homeomorphically irreducible tree, illustrating that a valid tree cannot contain a node that simply passes through with exactly 2 edges. The underlying lesson is that even the enumeration of tree structures is a graph theory problem, and getting the definitions of degree and isomorphism exactly right is what makes it solvable. And here is problem 2 in full. On the chalkboard, problem 2's statement reads, given a graph G, find the adjacency matrix A, find the matrix giving the number of 3-step walks, find the generating function for walks from point 1 to point J, and find the generating function for walks from point 1 to point 3. The worked chalkboard shows the adjacency matrix as a grid of zeros and ones, and A cubed computed as a matrix whose entries count 3-step walks. This is the key technical bridge for us. A graph can be fully represented as an adjacency matrix A, where entry ij is 1 if nodes I and j are connected, and powers of that matrix count walks of a given length. This matrix view of graphs is exactly what lets us bring linear algebra, and therefore neural networks, to bear on graph data. Now we are ready to define graph neural networks themselves. The central idea arrives with the phrase information passing between pairs of nodes, attributed to Hui, 2021. That single phrase is the heart of the entire model family. A graph neural network learns representations of nodes by repeatedly passing and aggregating information along the edges of the graph. Instead of each node being processed in isolation, each node's representation is updated using information from its neighbors. This is what allows the network to capture the relational structure. Let's make that message passing process concrete. Here, a GNN is broken into a feed-forward computation and a backpropagation training loop, with 3 conceptual stages shown across the bottom. First, we sample the graph neighborhood. We identify which neighbors of a node we will listen to. Second, we synthesize information, or features, from those neighbors. We aggregate their representations, often by summing, averaging, or pooling. Third, we predict graph context and label using the aggregated feature information. This 3-step pattern, sample, aggregate, predict, is the message passing framework, and it is trained end-to-end by backpropagation, just like any other neural network. Crucially, the aggregation step is designed to be permutation invariant. Because a node's neighbors have no inherent order, the function that combines them must give the same result regardless of the order in which neighbors are listed. This permutation invariance, and the closely related permutation equivariance at the node level, is exactly the symmetry that a plain feed-forward network lacks, and that makes GNNs the correct tool for graphs. Let's look at concrete tasks GNNs are good at. The layout is a grid of application panels illustrating the range of problems GNNs can address. Across these panels, the point is that a trained GNN produces useful embeddings that can drive many downstream tasks, from classifying nodes to predicting whether an edge should exist, to classifying an entire graph. Keep those 3 levels of task in mind: node, edge, and graph, because they organize almost everything we do with GNNs. Now let's see the full design pipeline of a GNN model. Credited to NVIDIA, 2024, this figure lays out the end-to-end pipeline. Step 1 is to find the graph structure. Step 2 is to specify the graph type and scale. The input graph is passed through a stack of GNN layers. The expanded box shows that each layer can include a sampling operator, a convolutional or recurrent operator, a pooling operator, and skip connections. Step 4 is to build the model using these computational modules.
producing outputs that can be node embeddings, edge embeddings, or graph embeddings. Step 3, the loss function, depends on both the training setting, supervised, semi-supervised, or unsupervised, and the task, node level, edge level, or graph level.
This diagram is the master blueprint. Choose your structure, stack layers that sample and aggregate, pool if you need a whole graph representation, and pick a loss that matches your task.
Before diving into specific GNN layers, let's connect graphs back to data we already understand.
The point here is that matrices and even text can be modeled as graphs, credited to Neptune.ai 2024. On the left, a line of connected nodes represents text as a chain graph.
In the middle, a regular lattice of green nodes represents an image as a grid graph, where each pixel connects to its neighbors. On the right, an irregular colored network represents a general graph.
The double-headed arrow between the image grid and the network emphasizes the key insight. A grid is just a special, highly regular kind of graph.
This means the convolution we already know for images is a special case of a more general operation on graphs, which sets up the next slide beautifully.
Let's make that connection between GNNs and graphs explicit.
Here, convolutional neural networks are reinterpreted as graphs. On the left is a 5x5 grid of pixels with a 3x3 filter sliding over a highlighted center pixel and its 8 neighbors.
On the right, the same grid is drawn as a graph, where each pixel is a node connected to its neighboring pixels, and a highlighted center pixel, labeled as pixel 24 with RGB features, receives edges from its vicinity.
The update per pixel recipe is stated clearly. First, transform every neighboring pixel's state by some weight. Second, add everything together.
This is exactly a convolution, a weighted aggregation over a fixed neighborhood. But notice the crucial difference. On an image, every pixel has the same number of neighbors arranged in the same geometry, whereas on a general graph, neighborhoods vary in size and have no fixed layout.
That is precisely why grid-based GNNs don't directly apply to irregular graphs, and why we need a convolution that works on arbitrary neighborhoods. That generalized convolution is the graph convolutional network. Turning to graph convolutional networks, or GCNs, from Kipf and Welling, ICLR 2017, with related earlier work by Duvenode and colleagues, NIPS 2015, and Lee and colleagues, ICLR 2016. On the left, we consider an undirected graph and calculate the update for a single node, highlighted in red, aggregating messages from its neighbors, including a self-loop.
The update rule is written as h minus I at layer L plus 1 equals sigma of h minus I at layer L times W, 0 at layer L, plus the sum over neighbors, j of 1 over c minus I minus j, times h minus j at layer L times W1 at layer L.
In words, a node's new representation is a nonlinear function of its own transformed features, plus a normalized weighted sum of its neighbors' transformed features, where Cij is a normalization constant.
This layer-wise rule is often written compactly in matrix form as h at layer L plus 1 equals sigma of d to the minus 1/2 times a hat times d to the minus 1/2 times h at layer L times w at layer L. Here a hat is the adjacency matrix with added self-loops, d is the degree matrix, and the symmetric normalization by d to the minus 1/2 on both sides keeps the scale of features stable regardless of how many neighbors a node has. The desirable properties listed on the right are exactly why this works so well. Weight sharing over all locations, invariance to permutations, linear complexity in the number of edges, order E, and applicability in both transductive and inductive settings.
Note also that scalability comes from subsampling messages, referencing Hamilton and colleagues' NIPS 2017. And that reference is GraphSAGE, whose whole idea is to sample a fixed number of neighbors and aggregate them, so the method scales to enormous graphs where a node might otherwise have thousands of neighbors.
Now we add attention to graphs,
titled Graph Neural Networks with Attention, and credited to Kamani and colleagues, 2024. This slide shows the core idea of attention on graphs. An input graph has a central node xi with neighbors xi minus 1 through xi minus 4, connected by edges y. The representation is pushed through two encoding paths, a self-attention path that produces a self-coefficient from xi, and a neighboring attention path that produces local coefficients from the neighbor relationships. These are combined through a softmax to produce attention coefficients, denoted xij. The essential idea is that not all neighbors are equally important, and instead of using a fixed normalization constant like the GCN, an attention mechanism learns how much weight to give each neighbor based on the features themselves. Let's see the formal graph attention network, or GAT.
Continuing on attention, this reference is Monti and colleagues, CVPR 2017, Hoshen, NIPS 2017, and Velikovic and colleagues, ICLR 2018, whose figure is shown.
On the left, the attention mechanism takes a learned vector, A, applied to the concatenation of W times HI and W times HJ, passes it through a leaky real U and a softmax over neighbors to produce the attention weight alpha ij. The central figure shows node H minus 1 attending to neighbors H minus 2 through H minus 6 with different attention strengths alpha, then concatenating or averaging across multiple attention heads to produce the updated representation H minus 1 prime. The update equation is Hi prime equals sigma of 1 over k times the sum over k attention heads of the sum over neighbors j of alpha ij at head k times w at head k times hj. And the attention coefficient alpha ij is the softmax, xp of leaky real u, of a transpose times the concatenation of whi and whj, divided by the sum over all neighbors k of the same quantity.
The pros are that there is no need to store intermediate edge-based activation vectors when using dot product attention, and that GAT is slower than GCNs, but faster than GNNs, with full edge embeddings.
The cons are that it is most likely less expressive than GNNs, with explicit edge embeddings, and it can be more difficult to optimize.
The big picture is that attention gives the model a learnable, data-dependent way to decide which neighbors matter most. The same intuition we saw in transformers, now applied to graph structure.
Let's unify these variants into one framework. Here, 3 flavors of GNN layers sit side by side, updating a central node, XBI, from its neighbors, XA, XC, XD, and XE. The convolutional flavor uses fixed coefficients, CBA, CBC, and so on. The weights depend only on the graph structure.
The attentional flavor replaces those with learned attention weights, alpha BA, alpha BC, and so on. The weights depend on the node features.
The message passing flavor is the most general. Each neighbor sends a computed message, MBA, MBC, and so on, which can be an arbitrary learned function of both nodes. This is the elegant unifying view. Convolutional, attentional, and message-passing GNNs form a hierarchy of increasing generality, and GCNs and GATs are just specific choices within it. So how do we actually put these models to work on real problems? Now, how do we use a GNN or GCN for real problems? The answer depends on whether we want to predict something about individual nodes, about edges, or about the whole graph. Let's make that precise. Now we consider classification and link prediction with GNNs and GCNs. The input is a feature matrix X, which lives in R to the n by E. That is n nodes each with an e-dimensional feature vector, together with a preprocessed adjacency matrix A hat.
The pipeline shows the input graph passed through hidden layers with ReLU nonlinearities, following the propagation rule H at layer L plus 1 equals sigma of A hat, times H at layer L times W at layer L, producing an output embedding Z, which equals H at layer N. 3 tasks branch from that output. Node classification applies a softmax to a single node's embedding Zn, following Kipf and Welling ICLR 2017. Graph classification applies a softmax to the sum over all node embeddings. That summation is the readout, or pooling step that collapses a variable size graph into one fixed vector. Following Duveneau and colleagues, NIPS 2015. Link prediction estimates the probability of an edge between nodes II and J as sigma of Zi transpose times Zij, essentially asking whether 2 node embeddings are compatible. Following Kipf and Welling's graph autoencoders, NIPS Bayesian Deep Learning 2016. So node level, edge level, and graph level predictions all come from the same learned embeddings, differing only in how we read them out. Let's look at a particularly practical training setting. Here we turn to semi-supervised classification on graphs. The setting is that some nodes are labeled, drawn as black circled nodes, while all other nodes are unlabeled, and the task is to predict the label of the unlabeled nodes. The loss is evaluated on labeled nodes only. L equals minus the sum over labeled node, indices L, of the sum over features F, of y minus L minus F times the natural log of C minus L minus F. A standard cross-entropy, but restricted to the small set of labeled nodes. Here the calligraphic YL is the set of labeled node indices, Y is the label matrix, and C is the GCN output after softmax. This is powerful because message passing propagates information from a handful of labeled nodes across the entire graph, so we can classify a whole network from only a few labels, which is exactly the situation in many global health datasets where labeling is expensive. Let's summarize the breadth of what GNNs can do.
This GNN and GCN summary shows 5 application domains through images: state machines, biological networks, social networks, molecules, and mobility and transport networks. The common thread is that every one of these is naturally relational, and a single architectural idea, learn node representations by aggregating neighbor information, applies across all of them. Let's continue that summary with the state of the field. The message here is that deep learning on graphs works and is very effective, and it is an exciting area with many new applications and extensions that are hard to keep up with. The examples shown are relational reasoning, from Santoro and colleagues, NIPS 2017. Multi-agent reinforcement learning, from Sukh-Bhattar and colleagues, NIPS 2016. And the GCN for recommendation on a 16 billion edge graph, from the Leskovec lab at Stanford, illustrated with Pinterest's recommendation of good versus bad matches from a source pin. The open problems listed are honest and important. Theory. We still lack a complete theoretical understanding. Scalable, stable generative models for graphs, and learning on large evolving data where the graph itself changes over time. Now let's ground all of this in concrete global health examples. Here is an example. Human Symptom Disease Network, from a Nature Communications paper published June 26, 2014, by Zhou, Menche, Barabasi, and Sharma. The figures show how disease-symptom relationships are extracted by bibliographic co-occurrence, linking diseases to symptoms. How a disease-disease network is built based on symptom similarity. How disease-gene relationships are extracted through shared genes and protein-protein interactions. And how a second disease-disease network is built on shared genes and first and second order protein interactions. The backbone visualization on the left clusters diseases into recognizable categories, like metabolic diseases and pregnancy complications. This is a beautiful demonstration that clinical knowledge itself can be encoded as a graph, and that graph structure reveals hidden relationships between diseases that share symptoms or molecular mechanisms. Here's one of the most celebrated applications. This example highlights the Cell paper, a deep learning approach to antibiotic discovery, by Stokes, Yang, Swanson, Yakola, Barzilay, and Collins. The graphical abstract and the in-brief summary explain that a trained deep neural network predicts antibiotic activity in molecules that are structurally different from known antibiotics, and among these it identified halicin, which shows efficacy against broad-spectrum bacterial infections in mice. This is a landmark result. A graph neural network operating directly on molecular structure discovered a genuinely novel antibiotic addressing one of the most urgent problems in global health: antimicrobial resistance. Let's see how that pipeline actually worked. Here the antibiotic discovery pipeline is laid out in detail. On the left is a directed message passing neural network that takes a molecule and builds up bond and atom representations. A new bond vector is formed by concatenation and summation over the molecular graph, exactly the message passing we have been studying. That model is trained on a set of roughly 10,000 molecules, then used to make large-scale predictions across a chemical landscape of over 100 million molecules, with iterative model retraining refining their predictions. The funnel on the right contrasts this with conventional small molecule screening, which caps out around 100,000 to 1 million molecules and has only a 1 to 3% hit rate. The comparison is the whole point. The GNN lets you virtually screen a chemical space orders of magnitude, larger than any laboratory could physically test, dramatically accelerating lead identification and optimization. Now let's situate today's lecture within the full course. You can see how the course has built toward this, from intro to AI and baseline machine learning, through neural networks, computer vision and vision transformers, sequence and language models, project definition, and generative adversarial networks. And today, graph neural networks. After this, we move into reinforcement learning, then limitations, fairness, and bias, applied global health case studies, regulation, and finally project finalization and design day. The lesson is that GNNs are one powerful tool among many, and the strongest global health solutions often combine several of these methods. For bibliography, chapters 1 and 2 of Graph Representation Learning by Hamilton, which is an excellent and freely available introduction to this field. For software, Google Colab at colab.research.google.com, which lets you experiment with graph neural network libraries like PyTorch, Geometric, or DGL without configuring a local GPU. Okay, let's wrap up. The main message from today is that graphs are the natural representation for relational data. Nodes and edges encoded through an adjacency matrix A, a degree matrix D, and a node feature matrix X. Standard CNNs and RNNs assume grids and sequences, so they cannot handle the irregular unordered structure of graphs, Graph neural networks solve this through message passing, aggregating neighbor information in a permutation invariant way, and updating node, embeddings layer by layer. Graph convolutional networks give us a normalized neighborhood average. GraphSAGE adds sampling for scalability, and graph attention networks let the model learn which neighbors matter most. From those embeddings, we can perform node level, edge level, and graph level prediction, using readout and pooling to summarize whole graphs, while staying mindful of practical challenges like oversmoothing, where stacking too many layers makes all node representations collapse toward one another. And in global health, these ideas are already delivering real impact, from symptom disease networks and protein interaction analysis, to patient similarity graphs, knowledge graphs, epidemiological contact networks, and the discovery of entirely new antibiotics.
Thank you for listening, and see you next time.